All right, so we're going to discuss concavity and the idea of inflection points. Recall a graph or a portion of it is said to be concave up if all secant lines are above the curve. Looking at a graph that we think to be concave up, if I take any 2 points on the curve and connect the dots, that's the secant line. The secant line is above, it's concave up. Just the basic definitions we have. Similar definition for concave down. Not showing up. Okay. We also know that if f double prime of A is greater than 0, then f is concave up at x equals A. In parentheses, I'll say f double prime of A less than 0 implies concave down, which is summarized in the picture we discussed, the second derivative rule, second derivative test of the comedy and tragedy of math. Okay, second derivative positive, you look like this, concave up. If it was negative, you look negative, you look concave down, you look like this. Okay? An inflection point of a graph is a point where the graph changes concavity. As a quick example, a function we looked at quite a few times now, f of x equals x cubed minus x. This implies that the derivative is 3x squared minus 1. And the second derivative is simply 6x. So when this function is positive, it's concave up. If this function is negative, it's concave down. Looking at a very quick sketch of said function, look at this graph here. Over here, f double prime is greater than 0, concave up. Over here, f double prime is less than 0, so concave down, which does jive with the picture we've seen before. Which looks something like that. These are at -1 and 1 and the origin respectively. Again, for x less than 0, to the left of the y-axis, this graph is concave down. Second derivative is negative. To the right, concave up. Second derivative is positive. Questions?
So will the inflection point be 0?
Question is where the inflection point is. The inflection point is stated either as phrase this either one of two ways. At x equals 0, or at the ordered pair 0, comma f of 0. Some people mean just the x value, some people mean the entire ordered pair. So if we have the idea of the critical point either being the x value or the ordered pair, same thing here. Now, it's not too hard to see where that happened here. For f to change concavity, the second derivative must either equal 0 or not exist. If I was talking about the first derivative, this would be the definition of a critical point. The idea here doesn't really have a great name. Simplest one I come up with is possible inflection point, abbreviated PIP. You can call them pips if you want. Okay, there's not a standard notation for these. We'll use pips, possible inflection point. So looking at our example, for f of x equals x cubed minus x, f double prime of x equals 6x, f double prime of x equals 0 or does not exist, implies that 6x equals 0 because it always exists, which gives me that x equals 0. Now, like we did with critical points, you still have to test this. To do that, you can simply make a table. X versus f double prime of x. Notice that at the value 0, the second derivative was 0. That's where it's possibly changing sign. Take a value to the left of 0, like -1, and a value to the right of 0, like 1. Plug them both into your second derivative. You get -6 and 6, which means concave down to concave up. This does show you have a change in concavity, so we do indeed have an inflection point.